Hello my friends, welcome again to my video channel. Today we'll continue our work on the PA brick of the TR7, and as you can see, that's already something prepared. So let's start. The board with the two power transistors and the two driver transistors is removed from the heatsink. Only some screws have to be unscrewed. Of course, we have to look for the isolation for the mica tabs here. This grease is very old, thermal grease. Thermal compound, we have to renew it, but that's not the topic in the moment. I took out the three resistors from one side where we have one original and the two other. I will see which types they are, and I also removed meanwhile the inductivity, this little choke from here. The other one is here. I've seen that this one, or counted, has 15 turns, and this one has only 14 turns. And when we have a thorough look at it, we can see, where is it? Here is it. That there's obviously some solder activities, and the neighbored wire is also black. Maybe there happened something. And now we have here only 14 turns. Seems like someone has taken out one turn and resoldered it. I will completely rewind it with a new copper wire. It's 0.3 millimeter, and I have the same 0.35 millimeter. Sorry, what I'm telling, it is nonsense. 0.25. 0.25 something, 0.3 millimeter. And this wire, which I have here, has also 0.25 something. It's okay. The diameter is not so critical. There is no high current flowing. It's a very old one. I don't know where I have it from. Date 23rd of May 1960. Okay. I can use it, of course. And indeed, as I've assumed, there was a repair. It was soldered together like this. Not so good idea. It should be rewound, but okay. That's it. I will add additional, or not additional, I will add 15 turns now. The coil is rewound, 15 turns. By the way, when you are counting turns, you have to count the number of wires which go through the center of the core. Not outside, inside. So this is the first one which goes in, second, third, and so on. And the last one is number 15, this one. When you count them outside, you only count 14. But which go through is one more. This has to be counted, and then we can reinstall it. The choke is resoldered again, and now I will use some drops of hot melt glue to stabilize it. The other one was also, as I see, stabilized with some drops of hot melt glue, so this is the best choice in this case. What are we doing here? I use my small vector network analyzer I have. It goes up to 3 GHz, theoretically. Usable, I think, up to 1 GHz, but that's not important. I will use it up to 200 MHz from 0. I will measure some resistors I removed from the PA brick, just to see whether there are real resistors over the frequency range, or whether they have any inductive or capacitive components. So let's say to measure the real and the imaginary component. Set real offset and imaginary offset. This is a well-known Smith chart. In the moment I calibrated it, of course, for short, open and load with 50 ohms. In the moment I have a short, and the dot is for all frequencies 0. The range is from 0 or 100 kilohertz up to 200 megahertz set. This is important first to have a calibration. When I now remove I will better show you the picture on the screen so you can understand it a little bit better, what's going on there. Switch off the light. You see here the dot. This is the point for 0 real and 0 imaginary component. That's the infinite point. Here we have the real part, it's a red line, 0 over the whole frequency, and IM S11 is this one, 0 over the whole frequency. Now I remove the short and guess where we land, where we are. We will be on this side. I take out the short. And the whole measurement now is here. These lines are useless because the result is infinite. But we are all here, and when I use a 50 ohm component or a resistor, so true 50 ohm without any problems, then we can see it here. This is the 50 ohm. First check is the resistor 2.2 ohm I took out of the PA brick. What is this? We measure here 2.2 ohms in the inductive component. By the way, this is 50 ohm, this is 1/3, 16.666, and this is 150 ohm times 3 and 1/3. It's a logarithmic scale, of course. The inductive component is not so big as it looks. When I go from, you see this red point, this is nearly 0 frequency. When I increase the frequency to 100 megahertz, 89, 90, 100 megahertz, we are here. We can measure 2.5 ohms, okay, in series. And this is 4.5 ohms, 2.2 or 2.4 measure the real component, inductive component, 4.5 ohms. This is inductive, this is capacitive. We have a little bit inductive component. I compared now to a resistor I would use as a substitution. This is 2.0. One moment, the clamps are not okay. Now it is fixed. And you see similar picture. No essential difference, it's 2.0. We have a 2.2 now measured. Okay, this is maybe the resistance of the clamps. And when we go up to 200 megahertz, we measure 3.11. Well, not a big difference, so both resistors are identical. I will swap them anyhow. And now to the next ones. This is the 10 ohm resistor. We measure here 11.1. I will measure it with the ohm meter. We see here a very small inductivity. It's obviously it's the original one, a carbon resistor. It's only 1.3 ohms in series at 200 megahertz. So this is a rather good resistor for high frequency application. As I said, a carbon one. And now let's check the 100 ohm resistor, which was in as a new resistor. And this is a new 100 ohm. This is 50 ohm, 150, this is 100 ohm. It looks as if the inductive component is very small. That's a consequence of the nonlinear chart. We have here curves, and this inductivity on this curve has a little bit more, and the result is 3.6 ohm, 99.9 impedance, and 3.6 it's 3 ohms inductive, but it is also a very good one. It's a new one, can be accepted. And now to this combination, two resistors 150 ohms in parallel. It was soldered on top of the board in parallel to the output transformer. It is this combination here. And these two resistors, 150 ohms in parallel, each has 2 watt. I will check this combination, it's the original one. And here we have the result. It's an interesting curve. No, I do not want an update. When I go down to 0 Hertz, the impedance is 94 ohms. Slowly. 150 ohm 2 times in parallel is 75, but not 94. Seems that these carbon resistors have a drift and they are a little bit capacitive with higher frequencies. We'll see when I go here, this goes down. This is a real component which gets less, 84, 81 ohms at higher frequencies, and we get a capacitive inductance of minus J12, minus 12 ohms capacitive. This one here, which is this blue line, 0, 40, it goes into the negative range, which is more capacitive. But the problem is it has not 75 ohms. And the measurement on the LCR meter shows 93 ohms and 1 kilohertz. At 100 hertz it has 91, 92 also, and not 75. So these old carbon resistors drifted, and this may cause a problem because these resistors are therefore attenuating any oscillation here, and they are designed for 75 ohms, and when they increase to 90 ohms could be a problem. So I have to replace them. I have chosen these two types, 150R metal film resistors, and let's have a look how they perform here on the Smith chart. And the result is perfect. 75 ohms and absolutely no problem with the frequency. We have here 75 ohms. When I move the pointer, we always have 75 plus 0.4 ohms, a very small inductive component, but this is not relevant. 0.5, half an ohm inductive now. Could be calculated. This is 8 microhenry. It's parallel equivalent. Okay, we are talking about series equivalent. Well, this can be used as a substitution for these old faulty carbon resistors. These two resistors are performing rather good, in spite they are a little bit coiled. I opened one of these resistors and you see the metal film is interrupted and it is coiled. It is coiled, that means it is aligned in the manufacturing process to get exactly 150 ohms. So a part of it forces the electrons on a longer way, so the resistance increases. The resistance increases, and this means it can be aligned to a certain value, so the tolerance is very narrow, but this causes an inductivity, and I will measure this one, only one. Note we have two in parallel, so the inductivity is considerably reduced, but one alone I think will have some measurable inductivity. We can see a little bit an inductive component at 200 megahertz. It is 4 ohms, 150 ohm precise, plus 4 ohms. So this is not relevant, and when we connect two in parallel, so we have much less inductivity as we have measured, so it's okay. This coiled resistor is still good up to 200 megahertz, but we have to know it. The surface is rather broad, so I think the inductivity is not so relevant in this case. But okay, it has to be considered for high frequencies. Now I'm checking some other resistors. First again I will check this with this multimeter now. This two resistors in parallel. They also have again 92.8, 93 ohms as measured before. It is real scrap. There are 3 remaining resistors in the other half of the push-pull configuration. 3 damping resistors. We can see them here. The first one should be 2 ohms, 2.0 ohms, and I can measure 2.83. Oh, it's my problem, sorry. Don't be 2.7. This has 0.1, or when I'm measured in this way, it has 2.6 instead of 2.0. The next one should have 100 ohms. Difficult to touch it. 127 instead of 100. Okay. And this one is 10 ohms. Is it true? 10 ohm, yes. Brown, black, black is 10 ohm. 8.3. Maybe the polarity is decisive. It's parallel to a transistor. Okay. Maybe I have a problem with the measurement with the transistor in parallel. Anyhow, I will take out all 3 resistors and then I can measure them again when they are out. Another important resistor which shouldn't be neglected is the resistor inside this choke. It is this one here. We have a, can see it, yes. This input voltage 13.6 volt, and here we have a choke which is supplying the power to the final amplifier, and this choke of course needs an damping and attenuation to prevent any oscillations, because here we have capacitors to ground, we have an inductivity, another capacitor to ground. This we could call a tank circuit or similar, with a resonance, and with a resonance, and this 15 ohm here inside is there to prevent this resonance. How to measure this resistor? Well, we could unmount everything and measure the 15 ohm alone, but I think there's a better solution. I found we also can use our vector network analyzer to measure this coil, this inductivity parallel with the resistor, and I show you how. I've unsoldered this combination RL on one side, took it out, it's easy, can be unsoldered. On the bottom side, you see, not difficult. And now we can measure with the vector network analyzer the parallel combination of resistor and inductivity. What do we expect? First, I have to calibrate this setup. Yes, I know these clip leads are not perfect for high frequency, and I see some of you guys getting stomach ache seeing this, but I have no better solution. I have to connect the inductivity resistor combination to the input here, so I will do this and I will calibrate it. This is a short. We see on the screen the short is not perfect. I will calibrate it with short, open and load. When I take the open one, open the leads, you see we are close here, and when I connect 50 ohms we will be there. I will redo the calibration and then we can start the measurement. We see here the recalibrated unit is connected to the coil and the resistor, and what we see is what we can expect. We see here a half circle. That means the frequency is not high enough. But very important, in the parallel equivalent we see here 18 ohms, and when I go to another frequency 17, 16 at very low frequencies, okay, I think we have a problem with the low frequency in the measurement accuracy. And at higher frequencies, when the coil is not relevant any longer, we go down to 16 ohms. We are at the frequency of 7 megahertz now. When they go up to 10 megahertz, we come to this 16.8 ohms. We can see there also, this is a red one, set real is 16 ohms. But I think this is a series equivalent. Yes, that's forget it. It's only for series. This is a parallel equivalent. That's important for us. So we have here a circle, and when we would increase the frequency further, the circle would go through this clock impedance. Hard to clip it. Okay, and this is as we heard 50 ohms divided by 3. It's 16.8 ohms. So this circle would close, and with very high frequencies we would get capacitive and come back, but we have no real capacity at this frequency. There's only a coil, so we can stop it here, but the result is clear. We have 17 ohm parallel and some 100 nanohenry also in parallel, and at lower frequencies we have 400 nanohenry, 19 ohm. I do not believe that this measurement here is okay, but I think this is better. 17 ohm, 16 ohm. So we can say that inside this coil the resistor, the 15 ohm resistor, is also okay, and we can use such a network analyzer also as a RLC meter, but with various frequencies, not only with the standard frequencies of some 100 hertz or kilohertz. We can go up to the megahertz range with this unit and see in the Smith chart where we are. It's very informative. We are in the inductive range, which is obvious, and this circle would go here through this point, but then we would need a parallel capacity. If this resistor wouldn't be there, then our impedance would travel around this to infinite in the resonance point and come back here with capacitive and go to the zero again at very high frequencies. This would be a behavior of a parallel resonance circuit. Well, you see, we could discuss about this vector network analyzer for hours. I will stop it now. I will say the resistor is okay, and we will focus on the topic here, and this is to bring this old TR7 back to life. Now we are at the end of part 7 of the videos about the TR7. We have seen that in the PA brick there are some resistors, some carbon resistors which drifted away. Maybe this is a cause for the instabilities. We will see. In the next video footage we will swap these resistors, do some tests, also check the characteristic of the low pass filter. Maybe if there's a problem in the low pass filter, not only in the PA brick. So you see, there is still something to be done. Stay healthy, stay tuned, see you on this channel.